Good evening, ladies and gentlemen. Welcome to the Scientific Conference, annual event held by the English Department of the Physical Faculty. My name is Yuri Gurikov, and I'm going to be the host of today's event. This conference, the aim of this conference is to perform and to practice public performance skills which are necessary for the future scientific activity which supposes performing in international conferences. Today we have 13 speakers on the agenda. Let's greet the first speaker. She will tell us about luminescence of nanoparticles.
Um, Good morning, ladies and gentlemen. I hope you can see my presentation. Do you?
Yes.
Yes, we see.
Good morning, ladies and gentlemen. Evening, ladies and gentlemen. My name is Fidelina Anna. I'm a third-year student from the Physics Department of Moscow State University, and today I'm presenting you work that observes interactions between lanthanide-based nanocomplexes and surrounding molecules. The outline of my talking is follows. General information about biomarkers, the goals of my research and the subjects of the investigation, some important experimental results, and finally, the summarize for further research. It is well known that lanthanide-based nanocomplexes seem to have a great potential in the field of optical devices and biomedicine. At this point, I can notice the following luminescent materials. For example, fluorescence proteins and organic dyes. Most of these conventional materials exhibit luminescent emission with Stokes shift. That means they emit low energy photons under excitation with higher energy ones. But what are the differences between UCMPs and other biomarkers? The nanocomplexes we are talking about are primarily the particles that can generate anti-Stokes luminescence. In this case, the emitted photons have higher energy than those used for the excitation. I shall start with the main advantage of upconversion nanoparticles. Due to the great number of transitions between the energy levels of lanthanide ions, there is an ability to change and control luminescent characteristics of complex by selecting different impurity ions. We have a chance to choose a complex with luminescence located in 1,000 or 1,500 nanometers, being excited by 980 nanometers radiation. Near infrared range is not toxic, and it is valuable for in vivo use for deep penetration. Many biomarkers mentioned before are excited by ultraviolet or visible range, which causes an autofluorescence. You can see it in the picture. In other words, we not only excite the luminescence of nanoparticles, but also generate natural fluorescence of biological tissue. That can overlap the spectrum of UCNPs. And in case of near excitation, the luminescence of the complex situates in a field free of autofluorescence. Particles revealing anti-Stokes luminescence are called upconversion nanoparticles, as I've already mentioned before. There are several ways to generate anti-Stokes luminescence in lanthanide diped nanocomplexes, and the most effective and the most simple one is to use energy transfer from one luminescent center to another. For example, the ytterbium and thulium ions along with ytterbium are often used as pairs, where ytterbium acts as a sensitizer because of its wide, large absorption cross-section. The advantages of these complexes are that they do not photoblank, have narrow and high emission peaks, and due to the great number of transitions between the energy levels of lanthanide ions, there is an ability to change and control luminescent characteristics of nanocomplexes. However, there are several cons apart from pros. Despite lanthanide-based nanocomplexes are being studied for several years now, some dependencies are still not clear. For example, the luminescent properties of UCPs depend on a variety of factors, and the ratio between activator and sensitizer is among them. Moreover, being injected in real biological environment, for example, blood or lymph, particles interact with different types of biomarker molecules and cell components. And I mean that thanks to UCLPs, we can detect lymphatic and blood vessels despite their complex and small sizes. But if we can be sure that we receive the clearest and the best signal. Nanocomplexes are also used to find and visualize tumors, but if we can get more from UCPs by taking interactions between lanthanide complexes and biomarker molecules into account. I wondered if surrounding influences the luminescent properties of CNSPs, and I turned to study of the interactions between lanthanide-based nanocomplexes and molecules in aqueous suspensions. The goals of and the objectives of the paper are to characterize the influence of surrounding molecules on UCNP's fluorescence, to measure the size of nanoparticles and to find out if they accumulate in the bottom, and finally to learn if the ratio of activator and sensitizers concentration influences their luminescence. The nanocomplexes may be represented as follows: a combination of inorganic crystalline nanostructure consisting of host material and one or several types of lanthanides. In this paper, the upconversion nanoparticles were observed in aqueous suspensions. A crystalline matrix was doped with two types of lanthanide ions in various concentrations. Ytterbium ions were served as sensitizer and thulium ions as activator. So the energy of ytterbium was transferred to thulium from the excited state. Sizes of the nanoparticles are also variable. Inert substances were used as solvents. The mixture of UCNP's powder and solvents occurred at the concentration of 2 grams per liter. To obtain anti-Stokes luminescence spectra, we used a diode laser with wavelength of 918 nanometers. The line width was about 2 nanometers. Here one can view the main characteristics of the devices. All the parameters kept the values constant throughout the experiment for not to influence their luminescence. Let's turn to a common picture that shows the dependence of intensity and wavelength. The most intense peak near 800 nanometers shows the transition between the next levels. To answer the question if surrounding molecules influence the luminescence, we should compare data required the same object of study in the different solvents. As it was found, DMSO provides a maximum intensity under the excitation peak and the water the minimum one. The spectra have been gathering for 30 milliseconds at least. Now let us turn to different solvents. We calculated the integral intensity of the main luminescent peaks during the experiment, and we found out that the object with more concentration has much more great intensity than the object with the less one. So to sum it up, we can notice the following. Time precipitation and maximum values of the luminescence intensity depends on both the solvent and the sample. That means the surrounding molecules and the intensity and the ratio of activator and sensitizer concentrations influence the glow. We should choose the combination of object with more concentration between activator and sensitizer in DMSO object for long experiments in future. However, there is an assumption that less concentration of particles in suspensions allows to reach plateau not only in water, not only in DMSO, but also in water, for example. Currently, experiments with a lower concentration value are being conducted in our laboratory, and we hope to receive positive results. That's it for the presentation for today. I'm ready to answer your questions if there are any of them. Thank you for your attention.
May I ask you a question? Why can we see the light in the cuvette even though the excitation wavelength is out of a visible range?
You can see here you can see the light, the blue light, and yes, we excite the ytterbium in near infrared range, but we can see then there is a transition to ytterbium that gives us a light in visible range. That is why we can view the luminescence in a cuvette.
Thank you very much. That's all.
May I start the
Thank you
presentation?
very much. Our next speaker has a research related to quantum computation. So welcome Petrov Ivan and his talk, The Accuracy of Single Qubit Operations.
Okay, let me start then. Good evening, ladies and gentlemen. Let me introduce myself. I'm a third-year undergraduate student of Physics Department of Moscow State University, Petrov Ivan. Today I'm going to present you the one of my latest research on the title of The Accuracy of Single Qubit Operations on Neutral Atoms and the Phase Noise Impact on it. The aim of this work is to study the principles and get acquainted with the experimental implementation of single qubit operations based on neutral rubidium atoms. This goal was achieved by solving the following main tasks. Firstly, I'll tell you about the principles of quantum simulator. Secondly, about measuring the accuracy of performing single qubit operations on a prototypical gate. The next point is to determine the contribution of phase noise to the total area of a single qubit Handama transformation, and finally, if possible, to create an electronic circuit with a low level of phase noise. Yes, this beautiful picture shows you the glow of a single atom inside a dipole trap. So I think now I'm ready to start. Let's start. Despite the idea of creating a quantum computer appeared recently, a real quantum race has already begun in the world. In fact, there is something to fight for in the field of quantum computing. According to the Church-Turing-Dutch principle, a quantum Turing machine can be used for computer modeling of systems with a large number of degrees of freedom. Quantum computers use the elementary base of a qubit, which is a two-level system. The state of a qubit is described by a wave function of the form beta equals alpha 0 plus alpha 1. There are many candidates for use in quantum computers such as superconductor qubits, ions traps, neutral atoms, etc. The neutral rubidium-87 atoms are insensitive to external fields and consequently to each other. Pre-cooled in a magnetic optical trap down to temperatures of the order of 100 millikelvins, the atoms are captured in an array of dipole microtraps and form a quantum computing core, on the basis of which further calculations are performed. Two hyperfine sublevels of each atom participate in forming of the logical states 0 or 1 of the qubit. The use of a system of several lasers allows performing operations. So, do you know that in a real experiment there is always some probability of error in quantum operations? Many external factors like radiation, noise in electronics, inaccurate selection of laser power, residual gas, temperature variations, etc., interfere with the control of a qubit. If you improve the experimental conditions, you can get rid of the influence of external lighting of the trap with atoms, reduce radio frequency interference, and temperature fluctuations. But it's impossible to protect a quantum computer from the noise that was originally embedded in the controlled electronic circuits. However, the noise of electronic that set frequency signals can be represented in phase and amplitude forms. In this investigation, the phase representation is used. You know that the phase noise fluctuations, such as sinusoid jitter, are caused by thermal noise, sharp noise, and flicker noise, and some other types of noise in semiconductor elements. Phase noise is defined as the spectral power density of a signal in a given frequency band. The amount of phase noise comparable to the total spectral power of a signal threatens instability of the frequency generator and, consequently, the frequency of laser radiation. When the generator is detuned from the resonant frequency of the atomic sublevel, an error is inevitably introduced into the result of quantum calculations. So, which results were achieved in this investigation? A spectrum analyzer was used to determine the spectral power of phase noise relative to the carrier frequency for a wide frequency band. The calculation of the error was divided into 3 steps. The first step was to create the block equations for the wave with phase fluctuations due to the signal. The next point was to solve these equations after transferring them into rotating coordinates, and at last to subject the state of a qubit to the single and double Hadamard transformations. But it's not as simple as it seems. The atomic sublevels undergo the AC Stark shift. That should be also taken into account. So let's pass over it to the experiment. Unfortunately, I'm rigidly timed and will say just a few words about the stop. In this part of it, you can see the magneto-optical trap, which is the source of atomic clouds. When the cooled atomic cloud passes through the area of electromagnetic field, the dipole moments of each atom start oscillating and become sensitive enough to form dipole microtraps inside the chamber. Then the 3 pairs of lasers. There are actually 3 lasers and each beam of which is mirrored. Make the cloud stay captured. And here you see the supply system. Are you ready for a simple exercise? If so, just compare these 4 graphs of signal spectrum and phase noise. On the first page, the signal for the minimal and maximal power is shown. On the second, the graphs of phase noise. The influence of higher harmonics should be noted there. This is the main cause of error. If you remember, the error was calculated for the double Hadamard gate. Here you can see the dependence of error percentage on the power of signal. X is the relative power and Y is the missing of the state Hadamard 0. Excellent, but the task isn't over yet. The spectral power density of high harmonics seemed great to me, so I had decided to create my own radio frequency filter with a sharp cut at 300 MHz and inject it into the generators chain. Here you see the schematic of this filter, and here the amplitude and phase responses. Dear colleagues, I have just enlarged your knowledge in physical realization of quantum computing, so allow me to tell you the results. Firstly, principles of operation and experimental implementation of single qubit gates based on neutral atoms in dipole microtraps have been studied. Secondly, the upper possible limit of the accuracy of operations on cooled neutral rubidium-87 atoms reached 99%. And at last, due to the lack of accuracy of single qubit operations on the prototypical gate in the digital frequency synthesizer circuit, a new radio frequency filter with a sharp cut at 300 MHz was constructed and integrated into the stop. It reduced the relative power of high harmonics of the carrier and the probability of error by several times. Thank you for watching and for listening. If you have got questions, I can answer them.
Okay, I have one question. So, how did you guess which elements to implement in your filter?
Well, a long selection of parameters was made because such complex filters are not verifiable to analytical calculation. If you place too much resistance, you'll turn off the signal, and vice versa. Too little resistance will make the signal grow near the cutoff frequency. But at last, the right combination of elements was found. Are you satisfied with my answer?
Okay, yeah. Thank you.
Any more questions?
Let's greet the next speaker. He will tell us about magneto-optical traps, the idea and realization of this method.
Good evening, ladies and gentlemen. My name is Shambretov Nikita. I am a third-year undergraduate student of Moscow State University, and my specialization is quantum electronics. I work at the Quantum Optical Technologies Laboratory under the guidance of my scientific advisor, Straub Stanislav Sergeyevich, the head of the Quantum Optical sector of Quantum Technologies Center of Moscow State University. Today, I'm going to tell you about my present-day work at the laboratory. Here is the structure of my talk. Firstly, I will start with introduction. Secondly, I will pass over to magneto-optical traps. Furthermore, we will discuss some experimental issues, and finally, I will make a conclusion. Let's start with introduction. We all know that computers and other electronic devices are incredibly useful. They are used in manufacturing, in science, and honestly everywhere. Moreover, I think there is no one who can imagine his life without smartphones. Such technologies save our time and money by doing plenty of calculations in relatively short time. But our demands are growing dramatically in the case of time, and now we want to process even more calculations with less durations. Working hard on that problem, scientists once have realized that we can use quantum effects to make great improvements in field of calculations. Without difficult explanations, I just assure you that quantum computers can accomplish some complicated tasks in a few seconds, whereas processing of the same tasks on classical computers may take days or even years. The example of such a task is number factorization. So that opportunity of great efficiency improvement was my motivation when I decided to go to the laboratory. Uh, okay, now let's pass over to magneto-optical traps. First of all, I want to tell you that my group works with cold atoms. Quantum theory shows that such atoms can be used in qubits realization. Qubit is a quantum analog of classical bit, and thus it represents an elementary computational block. So, for work with cold atoms, we need to confine them or trap them. So, there are many types of neutral atom traps, but today I want to tell you about one of them, namely magneto-optical traps or MOT. The idea of this trap is simple. Atoms with non-zero magnetic moment interact with magnetic field, and the greater the field is, the greater the energy of interaction becomes. So now let's imagine well-known anti-Helmholtz coils. It comprises of two parallel coils with current flowing in opposite directions. In such configuration, the magnetic field in the center, will be zero Gauss, and it will linearly change along the axis in the center. So magnetic particle, while it's shifting from the center, locates in non-zero magnetic field, and thus it acquires the interaction energy. So, as an outline, at the center the energy is zero, but while the atom is shifted, the energy is non-zero. Therefore, the atom seeks the center, the position of minimal self-energy. Congratulations, we've got an atom. Also, in such a trap, optical cooling is used, and so that trap gets a name, namely magneto-optical trap. Okay, now let's pass over. Let's speak about experimental issues. When we're back to the reality, we find many little difficulties. The simplest of them are Earth magnetic field and the field of still stuff surrounding the experimental set, like ropes, tables, screws, and so on. We must compensate that field. For this, we again use coils, but now in Helmholtz configuration. That configuration provides us with constant field in the center, and that constant field can be used in compensating of Earth magnetic field and field of still stuff. Another problem is the degeneracy of atomic levels with different projections of magnetic moment. An atom may transit to the state with the wrong moment and interact with Mott field in a different way, even do not interacting at all in case of zero projection. To solve that problem, we use so-called bias coils that also create constant field in the center and thus shift those levels correspondingly to projection. That shifting eliminates the degeneracy. So another thing I want to tell you that this shifting is called the Zeeman effect. Okay, dear friends, today I have told you about some advantages of quantum computations. Also, I told you about one common tool in the atomic confinement, MOD. Then we have discussed some experimental problems and their solutions. And now I'm ready to make a conclusion. Magneto-optical trap is an interesting scientific and engineering instrument of the future that allows you manipulate with atomic structures. Allows you to manipulate atomic structures. Application of this tool gives us an opportunity to create quantum computer and thus reach new technological level in the development of mankind. In addition, the trapped intermod atoms will be used for loading another trap called dipole trap or optical tweezer. That optical tweezer can be made extremely small and thus contain only one atom. That is perspective way of creating qubits. Well, my presentation has come to its logical end. In case there are any questions, I'm ready to answer them. And thank you for your attention.
I have one question. What exactly are the BIOS coils?
Okay, bias coils are just Helmholtz coils. It means they consist of two parallel coils with current now flowing in the same direction. That configuration gives us constant field in the center, and moreover, I can show it in the picture. These two coils, this and this, are bias coils. There is another interesting fact that Helmholtz coils must be placed in the right distant. Distant is equal to radii. Here we can see that the distance is bigger, but in for eliminating the degeneracy, it is okay. So bias coils is just Helmholtz coils, or those coils that that the distance between them are more than radii.
Thank you very much, Nikita. I think we don't have any questions. Um, Thank you for such a simple introduction to magneto-optical traps. Let's move on to the next speaker. We will consider adiabatic quantum computation. That's an interesting topic. Welcome.
Good evening, ladies and gentlemen. Let me introduce myself. My name is Mikhail, and I'm a third-year undergraduate student of Physics Department of Moscow State University. I would like to talk about an idea from the field of quantum physics. As you can see, the title states adiabatic quantum computation. I will tell you all about it, and since it is about quantum computation and we're all looking forward to the emergence of quantum computers, I think it's a topic worth paying attention to. Here's the structure of my talk. First, I will talk a little bit about some important theorem from quantum physics, and then I'll tell you what adiabatic quantum computation is and how it can be applied. Then I'll share with you results of my coursework, and then I'll make a conclusion. Dear colleagues, let's begin. So first, the adiabatic theorem. You can see the statement here, but in simple words, it means that if we have a system in its instantaneous eigenstate, and if we change slowly enough, the system will remain in its exact eigenstate. And for us, it means that if we have a simple system in its ground state and we evolve it slowly, we can get a system which is complex and it will still be in the ground state. And that is actually the whole method of adiabatic quantum computation. We get a system, a simple system in the ground state, and then we get a system that is more complex and still in the ground state. And this ground state gives us the solution to some problem. So the part is this theorem about a gap between the eigenvalue and the rest of the Hamiltonian spectrum means this. So this theorem only applies if there is a gap between the eigenvalue and the neighboring eigenvalues. So as you can see in the picture, the bold lines don't intersect during the evolution, which means that there's always a gap between them, and the adiabatic theorem is applicable. But the dotted lines do intersect, and if we had a system that evolves like this, adiabatic theorem wouldn't be applicable. So let's move on. There is a problem in computer science known as Boolean satisfiability problem. So suppose we have a set of n bits and a set of m Boolean functions, so that take values either of 0 or 1, so true or false. And all of them act on some bits from this set of bits of n bits. They can act not on all of them, but they only act on bits from this set. So the problem is to find the set of bits that satisfies all those m clauses. So all of those m Boolean functions have to return the value true, so 1. And let's see how adiabatic quantum computation can solve this problem. So we start with some simple initial Hamiltonian h sub b, and we construct the problem Hamiltonian h sub p, which is equal to the sum of Hamiltonians that correspond to all of the clauses. So each Hamiltonian that corresponds to a clause has to be in the ground state when the clause is satisfied. The problem Hamiltonian consists of the sum of those Hamiltonians. And then we set the evolution law to be this. So as you can see in the beginning, when time is 0, Hamiltonian is equal to the initial Hamiltonian, and when time is equal to the capital T, the final time, we get the problem Hamiltonian. Now, if we change the system slowly enough from one Hamiltonian to the other, according to this law, we will get the ground state of the problem Hamiltonian, which is the set of bits that we're looking for. So now let me share you with you the results of my coursework. I successfully simulated the adiabatic quantum computation on a simple model. So here's the model that I used. Suppose we have n particles with 1/2 spins, and their interaction is described by this Hamiltonian h sub 1. So each pair of particles interacts by the multiplication of their spin projection operators on the z-axis, and it's multiplied by some constant, and these constants together form a matrix. So now let's put this system in a magnetic field that is parallel to the x-axis, and we get another Hamiltonian h sub 0. And what we'll do, we'll start with the h sub 0 Hamiltonian, and we'll slowly turn off the magnetic field. And in the end, we'll get the h sub 1 Hamiltonian. So you can see there that when time is 0, we get the h1 Hamiltonian, h sub 0 Hamiltonian, and when time is equal to this, we get the h1 Hamiltonian, which is the final Hamiltonian. So now let's see some actual results. These are results for 4 particles, and this is how the initial Hamiltonian looks like. No need to be scared. It's just a matrix 16 by 16, and 16 is 2 to the power of 4, so 2 to the number of particles. And there are 2 main important elements. So the diagonal values represent the interactions between the spins of the system. And these 2.5s that scattered around the matrix are the interactions with the field. So this is the value of the field, which will slowly decrease to 0. And the final Hamiltonian, which is h sub 1, will consist only of the diagonal values. So let's see how it goes. We have this, we can easily calculate this Hamiltonian spectrum. Here it is. And now we find the ground state. We can see that this -10 is the lowest value here. So is it ground state? And we can calculate the exact vector that is corresponding to this eigenstate. So this is the ground state, a vector that corresponds to it. And now we know the initial state and the initial Hamiltonian, and we know how the Hamiltonian changes with time. So we solve the differential equation, the Schrödinger equation, using the 6th order Runge-Kutta method, but I won't get into this. So let's just see what the evolution gives us. So when we calculate the system evolution, we get our final state. After evolution is completed, we get this vector here. And we look at it, and it's not doesn't look nice. We know that our final Hamiltonian is diagonal, so its eigenvector should be trivial. So what did we do wrong? Actually, we didn't do anything wrong. Now we have to remember that in quantum physics, vectors actually correspond to states, and they can be rotated or multiplied by a phase. So what we have to do is rotate this vector, multiply it by some phase, so it becomes pretty. And after rotation, it looks like this. Let me move a little bit. Okay. So if we look at this here, we can see that all of these real parts of the vector. So first of all, the coordinates somehow became during evolution complex values, but actually they were complex values from the start. It's just that they had zeros as imaginary components. So it's all actually fine. And if we look at this vector, we can see that all of the real components are very, very small, except for these two ones. This is actually some calculational error. And the imaginary components also are very small, and they are all zero up to the 2 digits after the dot. So we can safely say that this vector is close to this vector here. And this vector here is actually, if we go back to the Hamiltonian h sub 0 and we take out all of this 2.5, and we get the h sub 1 Hamiltonian, which is diagonal, we can its eigenvalues will be here along this diagonal. So the lowest eigenvalue will be minus 1.6, and the corresponding eigenvector will be this right here. So actually, this is the ground state of the final Hamiltonian. So now I'm ready to make a conclusion that the adiabatic theorem holds, actually, because it predicts that our vector in the end will be the ground state of the final Hamiltonian, and that's what we're observing. And that's basically it. I hope you found this topic interesting. If you have, thank you for attention. If you have any questions, I'm ready to answer them.
Thanks, Michael. I have one question for you. Can you tell me what actually contributes to error in the results?
Okay, there are two actual factors that contribute. So first, when we calculate this system evolution, we do it numerically. So we numerically solve the differential equation, right? And it is not absolutely accurate. It's not the absolutely accurate way of calculating a function, right? It always has some error in it. So using more computational power, we can actually reduce this error. And another factor is that adiabatic theorem works only when we change the system infinitely slowly. But we don't change it infinitely slowly, and we can slow the evolution down, but we will need more time to calculate it, to calculate the result this way. So all of these errors actually can be reduced by using more computational power. But to show these results, I think this type of error works pretty fine.
Oh, okay, got it. Thank you very much. And let's pass over to the next topic. It's about detection of quantum vortex, new methods in this field. Welcome our next speaker.
Good afternoon, ladies and gentlemen. My name is Mikhailov Pavel. I am a third-year undergraduate student of Lomonosov Moscow State University. I specialize in semiconductor and cryo-electronic technologies. Today, I'm going to make a report dedicated to applying non-mechanical resonators for quantum vortex detection. Here you can see the structure of my report. Firstly, I would like to tell you about the laboratory of cryo-electronics, where I make my scientific research. Secondly, I will consider the subject in question. Thirdly, I will shed some light on current aims that I strive to achieve and some difficulties that I meet. Further, the latest results will be shown. And finally, I will make a conclusion. Dear colleagues, let's start, shall we? To begin with, I would like to tell you about the laboratory I work at. Primarily, our lab makes experimental research. There are two heading directions of work, closely connected with each other. The first one implements production and usage of single electron transistors and their applications. The second one is related to low temperature measurement of nanoelectronic devices. Also, we have such study directions as probe microscopy and superconducting materials. The lab provides researchers with the state-of-art technologies that allow conducting experiments at the highest degree of accuracy. Now, let's pass over to my personal research. Nowadays, my area of research consists of nanomechanical resonators and their applications to measurement of quantum vortices in superfluid helium-4. To be short, a nanomechanical resonator is a double-clamped bridge made of elastic material that has two dimensions comparable to several hundred of nanometers. Such a device can be driven to oscillate at very high resonant frequencies up to gigahertz and can have quality factor Q over 1,000,000. It is amazing, isn't it? Our colleagues put this device into superfluid helium-4 in order to detect quantum vortices. I would like to explain you what it is. You can see the phase diagram of false helium on the slide. As we cool helium lower than 2.17 Kelvin at pressure of 5 times 10 to the minus 3 MPa, helium becomes superfluid, and then it can be divided into two components. One of them is normal component that has non-zero viscosity, and the second one is superfluid component that has zero viscosity. In order to understand the nature of quantum vortices, let's consider next example. When not superfluid helium rotates in a centrifuge, its surface looks like a parabola with definite depth. Dear colleagues, look at the picture A. Now, let's cool helium down lower than lambda point. We can notice that superfluid component doesn't have any viscosity, so it will not interact with the walls of the centrifuge. That means that it won't be involved in rotation. And due to this, we can conclude that the depth of the parabola in this case will be defined only by rotation of normal component, and it has to be smaller than in high temperature example. But actually, the depth of the parabola tends to be the same like in the high temperature example. This surprising result can be explained by the formation of quantum vortices in superfluid component. These vortices have discrete values of angular momentum proportional to Planck's constant. They are formed in the way that movement of superfluid and normal component totally simulate the movement of fully viscous helium. Now, dear colleagues, let's change the topic a bit and speak about current aims. The main challenge for our research is to develop the process of nanoresonators fabrication that includes several tasks. Firstly, we have to develop theoretical estimations of resonant frequency dependence on geometrical and material parameters of nanobeams. This will allow us to manufacture beams with the precisely predicted resonant frequencies that is crucial for quantum liquids explorations. Secondly, we have to find out the way how to use a theoretical estimation in order to construct beams with the precise resonant frequencies. And thirdly, we need to increase the reproduction efficiency of final devices. Now, and here inevitable question arises. Why is it so hard to calibrate manufacturing process? We have more than 10 technological steps during the process of manufacturing, like it is shown in this slide, and every of them has each parameters of operation that lead to different results in outcoming product. By the way, parameters of manufactured nanoresonators may differ from what had been predicted before the fabrication due to some inaccuracy of instruments. Now I would like to share our progress in achieving those aims. We have made a theoretical research related to the resonant frequency formulae. During this research, we have got an estimating equation shown on this slide. Also, you can see the result of applying the formulae for nanobeams, theoretical dependencies of resonant frequencies on geometrical parameters of beams. Also, we are working on increasing the production of final devices. Currently, we have not so proper efficiency because we're integrating a new technological process of manufacturing. We're still conducting lots of experiments to calibrate manufacturing process. And it has one significant feature. This process is time-consuming. It can take up to 1 week to make a batch of samples. So this integration is going not so fast as we would like. Dear colleagues, my performance has come to its logical end. I do hope that during my talk, I enlarged your knowledge in the sphere of nanoelectronic devices and their applications. To conclude, I would like to stress that this research is worth carrying out in order to understand the nature of quantum liquids to the full extent. Thank you for your attention. If you have any questions about my scientific work, I will be glad to answer them.
Pavel, I have a question. Can you explain me what is the principle of nanobeam detecting quantum vortex?
Actually, this is one of the most important and popular questions, so I made a special slide for it. We put a nanomechanical resonator in the constant magnetic field B that is perpendicular to the plate of nanoresonator. There are X and Y axes. Also, we put nanoresonator into AC circuit in order to excite forced vibrations. And when the frequency of AC current equals resonant frequency for this beam, the response from this electrical system is maximal, that is measured by electric circuit analyzer. And then, when a quantum vortex interacts the beam, this resonant frequency changes that is also measured by electric circuit analyzer. And that's how we detect quantum vortices.
Thank you very much.
Thank you, Pavel. Our next speaker, she will tell us about the problems of venous thrombosis, which is crucial in medicine. So welcome our next speaker.
Okay, good evening, ladies and gentlemen. My name is dept Anna. I'm the student of Moscow State University, the Faculty of Physics, and I'm the third year undergraduate student. Today, my talk will be connected with the problems of venous thrombosis, as you can see on your slide. First of all, let's talk a little about the structure of my topic. I'm going to begin with the introduction, then I'm going to move to the main part, and we will look into venous valves, flow patterns, and important blood components, and their role in venous thrombosis, and also I'm going to move then to the conclusions. Let's start. The problems of venous thrombosis is one of the most pressing in our time, and according to different resources in their websites, a lot of people suffer from this disease. The occurrence of venous thrombosis is influenced by a huge number of factors, such as physical factors, biological, chemical, and today we're going to look into some of them and try to understand how this process is going on. The aim of this work was to observe venous thrombosis using the methods of physics at the role of venous valves and venous flow in the formation of clot, the valves and their cycle of movement, the basics of hemodynamics, and other principles, other biological principles. The initiation and spread of venous thrombosis is poorly characterized compared to other types of thrombosis. Have you ever heard about other types of thrombosis? Well, basically, it's just two of them, venous and arterial. And scientists are not always interested in venous thrombosis because it's really hard to understand and it's really hard to make in vivo models. This is, so venous thrombosis is really poor characterized, and this is due to the absence of animals and in vitro models that reproduce the hemodynamics and microenvironment of the venous valves, from which most venous thrombosis in humans occur. It is believed that venous thrombosis begins at the venous valves, and here on this slide you can see the structure. It's kind of a model and the structure of venous valves. So here is the normal blood flow, deep vein thrombosis. You can see on the left side some clots which are situated near the wall, and embolism. So embolism, it's the last stage of venous thrombosis when this clot, which is formed from various blood components, this clot is going to move further with the help of bloodstream, and it's going to move in our lungs and in our heart, and this how premature death is occurred. And on the left side, you can see just like physiologically where the veins and these valves are situated. Well, so that was a kind of biological part, and let's try to observe flow patterns with the help of mathematics and probably see some models. The liquid away from the wall has more inertia and is able to overcome the pressure gradient and continue to move downstream. We represent the Reynolds coefficient, which you can see on the bottom of the slide, where ρ is the density of the liquid, nu is the viscosity, v is the average speed, and r is the characteristic size. Thus, after looking carefully at this expression, we can come to the conclusion that the more viscosity forces play a role in the movement of blood, which means that for a high Reynolds coefficient, the more coefficient is, the more viscosity forces are playing part. Um, the viscous forces are acting on the liquid in the near wall region, reduce the inertia so that it cannot overcome the pressure gradient, causing recirculation. On the left side, it's more obvious to see how this recirculation starts. So bloodstream is usually going straight, but in these valves, it's going to recirculate. And in most of the cases, some problems which are led to deep venous thrombosis are happening in this region. So because this circulation is not really, it's just a model. Here you can see just a picture, but in organism, in living cell, in a living organism, it's not, it doesn't work like this. And lots of problems are happening, are occurring here, and we can describe this with the help of mathematics and physics and try to make a model, as I did in my coursework. But I'm not really going to show you here the graphs and lots of mathematical calculations and stuff like that, just because I'm running out of time. But if you're interested, you're really welcome, and I will give you and I will send you these materials. Well, so there is no need to explain that thrombotic clots often break off and lead to pulmonary embolism with the development of pulmonary heart attacks, which may lead to the premature death. So basically, lots of people, most of the people in the world die not from different diseases, viruses, and stuff like that. They are dying because of various vascular and other types of problems. So pulmonary embolism is one of them, because if you suffer from other kind of diseases, the more you will probably die from pulmonary embolism or other types of problems with arterial thrombosis. So here is the embol. It's a kind of a blood clot, and it's moving down to the lungs and away to the heart and all over our organism. In general, consideration of the movement of blood flows through the venous valves is an extremely important task for constructing a model of the formation of a venous thrombus. Basically, the main problem is that we need to use lots of factors in this model: physical, biological, and chemical. And sometimes it's really hard to understand all the processes, especially if we don't have a real model in a real living organism. Here, just an example of this process. Like in a blood clot, you cannot only see the platelets or other blood components. You can see neutrophils, lymphocytes, erythrocytes, as you can see here on this slide. So lots of lots of blood components play an important role, and we need to describe all of them. As you can see here in the picture, they also have their shapes. They also are moving through our bloodstream, and all these kind of movement and all this kind of interaction must be taken into consideration and then described later. That's the main problem, and that's a real tough question for the future. So in conclusion, I really want to make this conclusion, but firstly, I want you to see this diagram and once more emphasize how many people suffer from this disease and how many premature death and how much premature deaths are caused by this disease. So in conclusion, I would like to say that not only the dynamics of valve movements play an important role in clot formation, hemodynamics of blood flows, the role of neutrophil traps, which can be described further, play one of the important roles in the development of venous thrombosis as well. The further goal is to create the whole model. And why are we trying to create this model? Why? Just because the right model will simulate the right processes which are more connected to our life organisms, and that will help doctors and other specialists to create the right treatment against this disease, and probably to find solution how to stop pulmonary embolisms and other tough problems which can lead to the death. So that's all for now. Thank you for your attention, and in case you have any question, you're really welcome to ask me. Yes, and I have a question. You were talking about blood clots, and where else in the body blood clots can be formed?
Well, that's an interesting question, and I want to give you an example. For example, now my work is not connected basically to the venous thrombosis, but it's more connected to different blood clots which are formed in our body if we have such a tough disease such as cancer. So cancer can influence the formation of blood clots in our organisms, and as for me, I study now how they are formed and where, and with the help of platelets and how these processes are working on. But still, let I also want to give you a more simple example. Like if you have an injury or you cut your finger or you have another type of injury, the blood is running out of your body, and then a small clot is formed with the help of platelets. And this is also can be considered as a clot, but in venous thrombosis, they are formed spontaneously in your organism, and that can lead to the death and other problems with your health.
Thank you.
Thank you very much.
Thank you, Anna. Um, I think every one of us has heard something about nanomaterials, but now you have a really cool opportunity to learn about it more. Welcome our next speaker, and his topic is related to nanoelectronic devices.
Good evening, ladies and gentlemen. Can you see my screen?
Yes.
Yeah.
So, good evening once more. My name is Sergey Pankratov, and I'm a third-year student of Moscow State University Physics faculty, Semiconductors and Microelectronics department. And I'm going to report to you about my scientific work at the department. So, let's look at the structure of my talk. The first thing I'll talk about will be scientific laboratories background. After that, I'll talk about single electron transistor. After that, nanoelectronics fabrication issues will be represented. After that, metal organic frameworks, then current works achievements, and in the end, I'll make a conclusion. So, dear colleagues, I'm ready to start. And at the beginning, I'd like to tell about my laboratory's background. So, Cryo-Electronics Laboratory was created in 1987 for the development of fundamental and applied research in the field of superconducting electronics, nanomechanics, and single electron devices. One of the directions of our work is to get around difficulties associated with industrial production of an electronic device. We are fighting for the production simplicity, convenience, and reproducibility. And my research is aimed at overtaking these obstacles. So it's well known that an electron is an elementary charge carrier, and a device capturing energy changes during the transitions of individual electrons will be the most sensitive one. Single electron transistor, SET, is an example of such a sensor. It can be represented as two capacitors with control potential in the middle. Under the condition of small thermal and quantum fluctuations and rather small potential in the middle, tiny systems capacitance will allow us to detect single electron tunneling. Otherwise, electron transport will be prohibited by Coulomb interaction, and which is known the Coulomb blockade. The blockade can be controlled with smooth changing island potential. So calculations show that the capacitance of the nanotunnel junction of 1 femtofarad corresponds to the working temperature of 0.1 Kelvin. I think that everyone agrees measurements are easy to be made at the room temperature, which is suitable for the capacitance 1,000 times less. It can be achieved at atomic or molecular scale in, for example, single atom transistor SAT. An island of SAT is a single atom, and this device has extremely high sensitivity at the room temperature. Unfortunately, there are some problems arise at the stage of the development of the device. Firstly, there is no easy way to put a single atom in a certain place with several angstroms accuracy. Secondly, there is no way to easily and reproducibly bring the electrodes to each other at sufficiently small distance to tune the characteristics of the device. So the idea of my work is to implement metal organic frameworks, MOFs, in SETs as active components. MOF, metal organic frameworks, are composite materials made of organic and inorganic parts. The organic part contains large polyfunctional organic molecules called ligands, and the inorganic one is made of metal atoms. Actually, these structures have been familiar to chemists since the 18th century, and they have already learned how to explore, produce, and customize their properties very well. So why did we choose MOFs? These structures have several properties we find useful. The first one is self-assembly. These two parts are attracted to each other, so they strike together in the correct lattice, so we don't need to artificially build the nanostructure we need. Secondly, is their properties customizability. Due to the diversity of metal organic frameworks, we can choose one with required shape, size, conductivity, and so on. So the idea of my work is to bypass complex and unique process of creating nanometer thin structure with using self-assembled MOF templates. The device is expected to look like in the picture. Metal centers are separated from the electrodes with long, non-conductive organic chain barriers. The parameters of this device allow electrons to tunnel through these barriers from the electrodes to the centers and from the centers to the electrodes. This composition will allow us not to only realize an SET, but also to program some Boolean logic on the MOF net. So, to date, optimal gold electrodes lithography template has been chosen for the metal organic framework growth. It includes size, layout, thickness, radiation dose, and so on. After that, the sample was transferred to the chemical department for the growth of the compound. Unfortunately, the compound wasn't observed on the electrodes using electron microscopy, but it is explainable because of insufficient resolution of the method. After that, a clean new chip was connected to the chip holder with tiny wires. It was made for the future measurements. And now the sample is ready for its covering with MOFs. Now, in the near future, I'm going to connect the sample to the measuring equipment to get the value of the working temperature, Coulomb blockade, as well as to program the simplest logical functions using the generic algorithm. So I have finished my talk and I'm ready to make a conclusion. Here, the research goal of my work was announced. The problem it covers and their relevance were also stated. There were theoretical basis and previous work results are presented, and further plans were announced. Thank you for your attention. If you have any questions about the project, I'm ready to answer them.
Thank you, Sergey. I have got one question to you. It's an interesting fact that you use gold as the material of the electrodes. Is there any profit? And how does it affect the cost of nano devices?
Yes, we use gold. Here you can even see it, gold, as the material of the electrodes. The first question was about the why it was used here. So this MOF that we use, we can see it here in this picture, is connected to the sample with a gold molecule, as we can see. So this MOF connects it, and it is fixed on the electrodes. What about the expenses? So it's not really expensive because we use a really thin layer of gold. You can see that here we used titan and gold. So very thin layer, about several nanometers, about 5 or 6, I don't remember. So that's why it's not really expensive.
Thank you.
You're welcome.
Thank you, Sergey. I think we can move to our next speaker. if you have ever wondered how to model blood flow of a human, the answer is in the next talk. Welcome our next speaker.
Good evening, ladies and gentlemen. My name is Georgi Bykov. I am a third-year undergraduate student of physics department. I specialize in biophysics. My scientific interest is human circulatory system and its associated processes. Today, I am going to present my latest scientific research in the sphere of hemostasis and thrombosis. Here is the structure of my talk. Firstly, I will briefly consider the circulatory system. Secondly, I will dwell on main points of my model. Further, I will show results. And finally, I will make a conclusion. Ladies and gentlemen, let's start, shall we? Circulatory system performs various functions in our body. It provides delivery of nutrients, oxygen, hormones, salts, removes metabolic products from the tissues, and takes part in heat exchange. The aim of hemostasis system is to protect the circulatory system, namely to stop the loss of blood after a rupture of blood vessel. Also, there is another similar process in our body called thrombosis. It uses the same resources as hemostasis, platelets and proteins. It occurs even in the absence of any mechanical damage to blood vessels, and the formation of the clot leads to a blockage of a vessel, which is why blood stops flowing to the tissues and even entire organs. So thrombosis is one of the main causes of human death. At the moment, the scientific community doesn't understand the causes that lead to the manifestation of one particular process, hemostasis or thrombosis. So we cannot affect on one process without affecting another. It is necessary to develop this field of science, learn to predict thrombosis, and find ways to prevent it. It is shown that the role of one Willebrand factor in the formation of hemostatic plaque depends on shear forces. So in my coursework, the model was being developed to study shear rate near the walls of damaged arteriole. In the model, I consider arteriole without coagulation. A little notation about definitions. Von Willebrand factor is a protein which provides attachment of platelets to the area of damaged vessel. It is one of the main blood clotting factors. Shear rate is a derivative of velocity in the direction perpendicular to the shear direction. Coagulation is formation of a blood clot. In this model, I consider several geometries of arterioles. The first one is needed to check if the initial values we use are in correspondence with biological norm. The others are needed to study injuries. At first scan, we can see healthy arteriole. It is a pipe of circular cross-section with thick walls and blood flowing inside of it. The second one is also a pipe of circular cross-section with thick walls and blood flowing inside of it. One end of pipe is cut and blood is flowing out of it into extracellular fluid, which is initially dormant. In the third geometry, arteriole is a pipe also of circular cross-section with thick walls and a round hole in the side of it. We will call it wound. Blood is flowing in arteriole. Arteriole is located once again in the initially dormant fluid, extracellular fluid. In this model, it is assumed that blood and extracellular fluid are single-phase, viscous, incompressible Newtonian fluids. The inlet pressure is an initial value and it is constant. Blood flow is laminar, temperature is constant, and blood flow is a basal flow. A little notation about definitions here. When we talk about single-phase fluid, we consider only fluid itself, there is no structures as platelets in it. Incompressible fluid means what fluid doesn't change its density. Newtonian fluid means that it obeys Newtonian law of viscous friction in its flow. And viscous fluid is a fluid that has a property to resist the movement of one part of a fluid relative to another. The main equation of a model is a stationary Navier-Stokes equation. We solve it numerically at the areas shown previously. The boundary conditions were pressures and velocities. And let's move on to a numerical solution. I have found an article where velocities and dimensions of mice ethereal were mentioned. You can see them on the picture. Calculations with those parameters were conducted on the intact vessel, and results fit exactly the numbers from an article. So the next step was to calculate velocities in wounded vessel. The maximum value of velocity was equal to 3.8 meters per second. The maximum value of shear rate was more than million inverse seconds. In now existing books about arteries and arterial blood flows, it is mentioned that the values of shear rate more than 5,000 inverse seconds are thought to be abnormally elevated. If we talk about the intact vessels, of course. Results don't seem natural, so the next step is to change the dimensions of ethereal within the biological norm and see if the model would show different results. We have three main geometry sizes: the length and radius of a vessel and the radius of wound. Now we will take all the parameters from basic parameters except length of a vessel. It will take the values from the following table, which you can see here. The table also shows maximum values of velocity in the entire volume and shear rate for given length of vessel. The columns in which data from calculations with basic parameter is displayed. I highlighted in green. The next table is about the change of radius of vessel. And the next, the last but not the least parameter will be changed, the radius of wound. We see that values of maximum velocities and shear rates are highly dependent on all three sizes of and the dependence is nonlinear. Moreover, maximum values of velocities remain being higher than expected. Dear friends, today I have enlarged your knowledge in the sphere of hemostasis. I am ready to make a conclusion. The above calculations give us reason to believe that large values of these velocities are normal physiological values, with reasonable assumption may prove to be a crucial feature that distinguishes hemostasis from thrombosis. Thank you very much for your attention. In case there are any questions, I'm ready to answer them.
Yeah, I have one. Why do you consider blood to be a single phase incompressible Newtonian fluid, even though it contradicts reality?
Oh, my goal is to give estimates of shear rate and blood loss through a wound in order of magnitude. It is not my goal to give an accurate quantitative prediction in each case. The present model is a good zero approximation, which, of course, should be developed in future.
Thank you.
Thank you very much, George. Let's pass over to the next topic. It is about medical imaging.
Good afternoon, ladies and gentlemen. I am Maxim Lenivkin, and I'm a third-year undergraduate student of physics faculty of MSU, and I specialize in physics of accelerators and radiation medicine. And I'm going to tell you about the technologies of medical imaging, which concerns my field of physics. First of all, I'll explain what imaging is. Then I'll tell you about radiography and ultrasonography. Furthermore, it will be mentioned how nuclear medicine is used. And finally, I'll talk about CT scans and MRI. So, dear friends, let's start, shall we? Medical imaging is the technique and process of creating visual representations of interior body for clinical analysis and medical intervention, as well as visual representation of the function of some organs and tissues. Obviously, tools of medical imaging are vital in diagnosing and treating a large number of diseases. Moreover, research and development in this area is a preserve of a variety of disciplines like biomedical engineering, medical physics, and computer science. Basically, there is a vast number of imaging techniques. Many of them are relatively new and still not widely used. In particular, this is the case for elastography, photoacoustic imaging, and thermography. Nonetheless, some tools of medical imaging have been used for a long period of time, and now almost everybody is acquainted with them. All in all, I'll tell you about the most widely used techniques, which are radiography, medical ultrasound, nuclear medicine, MRI, and CT scans. Let's start with radiography. It seems to me that everybody here knows what X-ray is. Generally, radiography is one of the oldest tools of medical imaging. The image is created using a beam of X-rays. It's produced by a generator and is projected towards an object. A certain amount of radiation is absorbed by the object dependent on the density and structural composition. Then, the structure of the object can be seen when the rays reach the detector. The technique is commonly used to do images of bones, teeth, and lungs. Unfortunately, this method can be used too frequently due to the threats of radiation. Moreover, I guess everybody has heard about ultrasonography, which uses ultrasound to create an image of internal body structures such as tendons, muscles, joints, blood vessels, and interior organs. Uh, Speaking about the way it works, the pulses of ultrasound are sent by a probe and they echo of tissues with different reflection properties. Reflected pulses are recorded and displayed as an image. Overall, it's fast and cheap technique, but it has a great number of drawbacks. For example, being unable to image structure behind bone or limited field of view. A more novel method of imaging is utilizing nuclear medicine. Particularly, it involves application of radioactive substances, but instead of recording radiation that is generated by external sources, the radiation emitting within the body is detected. Uh, in nuclear medicine, two most common imaging modalities are SPECT, which stands for single proton emission computed tomography, and PET, which is a positron emission tomography. In fact, both of the techniques are rather similar. They involve forming a three-dimensional image by having a radius isotope attached to a drug injected in the body as a tracer. And then the emitted radiation by the tracer is detected by gamma cameras. The main difference is that in a single proton emission uh, tomography, our tracer emits a single gamma ray, whereas in a positron emission tomography, a proton is emitted and a pair of gamma rays is released only after it reacts with electrons. However, this method of imaging is usually not enough to achieve a robust picture. That is why it's typically used in combination with a CT scan. So speaking about the CT scans or computed tomography, it's pretty similar to ordinary X-ray scan, but instead of taking one image, a combination of multiple measurements is taken from different angles to produce a cross-sectional pictures. Using this data, a three-dimensional image is created. Overall, this technology is vital at imaging complex bone structures because of its ability to reconstruct the area of interest in multiple planes. Furthermore, such scans are used to scan tissues of lungs and heart. Nevertheless, its major disadvantage is high radiation doses, which dramatically restricts the usage of such method. Alternatively, there is another technology that doesn't have this flaw. It's magnetic resonance imaging. MRI uses strong magnetic fields and radio waves to generate images of organs in body without using any radiation. Basically, it's a fantastic solution when imaging soft tissues. However, this method fails at picturing hollow organs like golders or lungs. Well, in summary, I've told you about medical imaging. I've discussed how radiography and ultrasonography work. Also, I've mentioned benefits and drawbacks of such technologies. Moreover, I've told you about nuclear medicine, and in the end, CT scans and MRI were regarded. In conclusion, I'd like to emphasize that medical images uses advances of many fields of physics and science. As I've demonstrated, all of such methods have both several pros and cons. I believe that in near future, more advanced technologies of imaging will appear, And the thing I like about medical imaging is that it's an incredible example of how work of scientists and engineers result in actually helping people and saving lives. Thank you for your attention. If there are any questions, I am ready to answer them.
Yes, I have a question. What method of imaging do you consider the most advanced one?
Well, as I've already mentioned, all of such methods have its pros and cons, some benefits and drawbacks. That's why all of them are used. But in my opinion, one of the most advanced is certainly MRI because, well, it doesn't have a lot of risk because it don't have any radiation. It's rather safe method. And also it allows us to get a very detailed image.
Okay, thank you.
Oh, okay. Thank you very much, Maxim. Let's greet the next speaker. He will tell us about hemostasis system.
Good evening, ladies and gentlemen. My name is Vladimir Kuratsev, and I'm third-year undergraduate student of the Moscow State University Physics Department. I'm specialized in biophysics. Our purpose this evening is to hear a presentation about a remarkably interesting and complex problem in modern science. Here is the structure of my talk. Firstly, we start with introduction. Then I will tell you something about hemostasis system, especially about dynamics of thrombus activator concentration and laminar flow, modern achievements in the understanding of this process, and about my model. Finally, we will try to make a conclusion. Since we have extremely limited time today, please hold your question until the end of the presentation. First, I will begin with some statistics. Nowadays, the first place in the number of deaths is occurred by diseases that lead to a violation of the hemostasis process. As you can see on the bar chart, ischemic heart disease and stroke take the first places at the top 10 global causes of death. Go to our next slide. Here I will begin with an overview of what biophysics in general is, and what the differences between biology, physics, and biophysics are. I think you should understand that the main purpose of biophysics is to explain biology description of living things using methods of physics. That will bring us to our next point. What is hemostasis in general? Hemostasis is a set of biochemical reactions and physics interactions in our body with the main goal to stop bleeding if there are some injuries. It can be solved with 3 steps. Platelet hemostasis, which is creation of blood clot like bottle cap. Plasma hemostasis, which is transformation of blood to more viscous state like jelly. And fibrinolysis, which is dissembling of a blood clot. It's remarkably interesting to know, but unfortunately, we will not discuss about this process today. Let us now talk about modern achievements in understanding of the hemostasis system and try to answer questions about the reasons concerning its construction. Today we know that platelets must be activated by some factors, for example, specific proteins, collagen, ADP, thrombin, and thromboxane, to start platelet hemostasis. It provides thrombus growth and stability. When platelet is activated, it becomes capable to connect with the place of injury. This process is called adhesion, and with other platelets. This process is called aggregation, with specific receptor-ligand interactions. Let us now turn to plasma hemostasis. This step is extremely complicated, but today we know enough to explain all biochemical reactions which provide making blood as jelly. You can see a cascade of chemical reactions at the picture. Even though it's extremely interesting, we don't have enough time to explain it. That will bring us to our next point. There are some actual questions that need answers. Why is the hemostasis system so complicated? For what reasons does the blood clot grow uncontrollably in some cases and cause danger for the organism? And how can hemostasis be controlled? Besides, there are a lot of other questions for scientists from all over the world. In this work, a thrombus model was built and implemented at the initial stage of platelet hemostasis for analysis concentration dynamics under conditions of laminar flow of one of the most important platelet activator, ATP molecules. The model was built in the COMSOL environment. A vessel is viewed in 2D with typical shear rates. At some distance from injury to a vessel, localized symmetrically in the middle vessel, there is a platelet aggregate consisting of a different number of platelets. Platelets are represented as perfect ellipses and impermeable for the flow and ADP molecules. There is an area under the damage filled with blood, with the same dimensions as the vessel. Two dense platelet granules expelled due to activation slightly above and below one of the platelets can secrete ADP into the bloodstream. There is a point near the first platelet intended for measurements. The calculations results you can see at the pictures were carried out under various conditions options: dense granule arrangement, platelet count, the presence or absence of injury, distance between adjacent platelets downstream or perpendicular to it. So, in conclusion, the following results were obtained. The reasons for the work of hemostasis, which includes large cascades of biochemical factors that may even seem redundant, are still not clear and require further study. Concentration of dynamic concentration of one of the primary activator platelets, ATP molecules, in modeling showed dependence on many physiological parameters. There are differences both in the absolute values of concentration and in kinetics of the process. The hemostasis system has a complex structure that requires detailed consideration to solve the problem of violations in its functioning, leading to death. My model is a ridiculously small step to the deep understanding, but it's the start to my own more complex studies. Thank you for your patience and attention. If you have questions, I will try to answer them.
Yes, Vladimir, I have one question. Firstly, I really enjoyed your detailed report. I have one question. I would like to know what is the difference between adhesion and aggregation?
Okay, I'm glad you asked that. Well, as I already said, adhesion is a process of connecting activated platelets with the place of injury. And aggregation is a process of connecting activated platelets to each other. I think the main difference between these processes is specific proteins, which is called receptors, on the surface of injury. They differ from the receptors and their lesions on the surface of platelets. I think is the answer for your question.
Thank you very much. Thank you very
much. Thank you, Vladimir. And dear colleagues, I'd like to share my own research with you. It is about geometric phase in quantum computation. Let me share my screen. Okay, good evening, ladies and gentlemen. My name is Yuri Gorikov. I'm the third year undergraduate student of physical faculty of Moscow State University, and I specialize in quantum electronics. At the moment, I'm doing a research at the Laboratory of Quantum Optical Technologies. My research is dedicated to a really popular, really famous geometric effect occurring both in classical and quantum physics, and it is called Berry space or geometric phase. I will call it GP in my talk, during my talk. Today I'd like to talk more precisely about quantum geometric phase, and here's the structure of my talk. At first, we'll talk about the origin of GP. Secondly, we'll move to the simple example of GP for one well-known quantum system. After that, I will tell you about the first observations of geometric phase, and finally, I'll shed some light on applications of geometric phase in integrated photonics. So, imagine we have any quantum system. We can describe all its properties and features with the help of its wave function. Wave functions are vectors in complex Hilbert space. The topology of this space can be much more complicated and sophisticated than the topology of three-dimensional flat Euclidean space, which is so familiar to us. During the evolution of quantum system, The end of the vector in this space follows certain trajectory. This way may be full of twists and turns due to the topology, and as the consequence, when the system returns to the initial state, the state we get differs from the state at the starting point. There will be additional phase shift factor. That is geometric phase. So to sum up, geometric phase is just a factor that depends on the trajectory of the system in Hilbert space. Now let's consider one of the simplest quantum systems. It is qubit. I hope every one of us has heard this word and has associations with quantum computers, Schrodinger's cat, and so on. For us, a qubit is just a vector in two-dimensional Hilbert space. The basis vectors of this space are called 0 and 1, just like 0 and 1 in classical computer. Um, it turns out that all the states of the qubit lay on the sphere, which is called Bloch sphere. The north pole corresponds to zero state, while the one state corresponds to the south pole. All the intermediate stuff is called superposition states, and it is just a linear combination of zero and one state. Imagine we have our system prepared at the North Pole. To make things more obvious, let's characterize the state of the system not only with the point on the Bloch sphere, but also with the tangent vector showing current phase state of the system. So if we start a rotation around x-axis till we reach the equator, then around z-axis for a quarter of the equator, and finally around y-axis to reach the initial point, we will see that tangent vector changed its direction. Actually, it turned 90 degrees. This is the effect of non-zero curvature of the sphere. Actually, Bloch sphere is a sphere which is not flat, though locally it really looks like a flat manifold, like our Earth. You may have a question in your heads. Do we have some relation between geometric phase and the trajectory of a qubit for this simple case? And the answer is positive and rather pure. If during the evolution of the system the trajectory covers the solid angle sigma on the Bloch sphere, then the value of geometric phase is just minus sigma over 2. This result is simple, but in my opinion it is really beautiful, because this is the pure relation between a real physical value and some geometric value, which is just a property of the space. So maybe for a moment you have an image that geometric phase is just a mathematical concept, but as a matter of fact, people used to observe it at the end of the previous century. The first experiments used one photon interference in Michelson interferometer. What was the idea of the experiment? In one of the branches of the interferometer, there were two quarter wavelength plates. If a photon passed through this branch, it would get additional phase shifts, which value depends on the mutual position of the plates. So slowly changing the value of the phase shift, which is exactly geometric phase, which value equals the opening angle of the trajectory on the Bloch sphere. They observed interference pattern as an effect of geometric phase. Nowadays, the design of any device using quantum effects should take geometric phase into consideration. For instance, in integrated photonics, where we use a really small system of waveguides to manipulate the state of a photon, if we neglect geometric phase, we won't get the correct distribution of intensities, and as a consequence, we'll have to waste time and materials to correct them. My work in the laboratory is dedicated to observation of geometric phase in system of waveguides, and also to find theoretical abilities to manipulate the state of a photon in these waveguides. I can tell you that we have already developed the scheme of the experiments, and we are to make it in a week or two. So we'll see what would happen. Dear colleagues, today I was really happy to share my personal research with you. And to sum up my talk, I'd like to state that progress and science are developing really fast. And how could one person imagine that some abstract small geometric effect in complex Hilbert space was detected in real life, and even more was applied for the technologies. I think the ability to understand how abstract mathematical ideas can be used in real life is priceless, just breathtaking. Thank you for your attention. I'm ready to answer your questions.
Well, I have a question. Can we think of a photon in the system of waveguides as a qubit?
Oh, well, it's a really good question. Actually, when we work with waveguides, we work with about two waveguides. And this is called dual rail coding. Um, Actually, photon is a qubit in this system. Imagine just two waveguides. These are two lines. If a photon is in the upper one, then we call it zero state. If it is in the lower one, then it is one state. So like on the Bloch sphere. And all the intermediate states of the photon of the lights are the states on the Bloch sphere. So yes, photon is a qubit in the system of waveguides.
That's incredible. Thank you.
Okay, I stopped my demonstration. Thank you for your question. And our next speaker will raise a really interesting topic of brain diseases, proteins, and how they are related. Welcome.
Good evening, ladies and gentlemen. My name is Murga Elizaveta, and I'm third year undergraduate student of Moscow State University Physics Department. I specialize in biophysics. Today, I'm going to present you my personal research connected with neurodegenerative diseases, and here is the structure of my talk. Firstly, I will consider what are the diseases and how they appear. Secondly, I will tell you about what protein has to do with it. Further, I will dwell on how this relates to chirality. And finally, we will speak about what's wrong with this protein and make a conclusion. Okay, now I will send you to the chat some terms difficult to understand. Second, please. It will be difficult, but interesting. Dear friends, let's start, shall we? Okay. Yeah. The brain is one of the most complex and fascinating objects, but also the least studied. It's also susceptible to diseases, and the mechanisms of these diseases is mystery. I said mystery because according to statistics, 85, imagine 85% of the diseases is sporadic and do not have a common mechanisms of occurrence. Another 15% are genetic and less than 1% are acquired. The most famous kind of these diseases are fatal family insomnia, Creutzfeldt-Jakob, Kur diseases, and Gertzmann-Straussler-Schenke diseases. The well-known diseases as Alzheimer, Huntington, and Parkinson have a similar principle of development. Neurodegenerative diseases may include convulsion, dementia, ataxia, behavioral and personal changes. All known brain diseases are incurable and fatal. The duration of these diseases ranges from 6 months to 2 years. But keep calm. The good news is that sporadically prion diseases occur on a global 1 case per 1 million per year. For the first time, such diseases were discovered in the middle of the century in cattle. There are spongiform encephalopathies of mammals, or mad cow, and the sheep scraping. The disease is called spongiform because as a result, mammalian brain turns in a sponge with air bubbles. It's in real life, it's look really creepy. And however, the causes of the occurrence became known only 2 centuries later. This happened because for a long time we are looking for a virus or bacteria but the pathogen was different from bacteria or viruses in its physical, biological, and chemical properties, and turned out to be a protein, later called prion. Term prion comes from two English words, protein and infection. Let's stop here for more details. I think that since high school biology, you have known that proteins are the most important components of living organisms. They consist of alpha amino acids. I can show it. Yeah, from alpha amino acids connected in a chain, and it is called a primary structure. Then this chain can turn into a helix. It's called a secondary structure. In the body, such helix exists in two conformation forms, alpha helix and beta helix. There are more complex protein structures, but we will not consider them. As important feature that you should know that in a huge number of staking forms in secondary structure and next structures, certain protein stacked in a certain way. In it's process called this process called folding, but mechanisms of folding has not been studied. Now, let's change our topic and speak about chirality. If you study a structured object, in many of them, you will be able to determine such type of symmetry as chirality. Chirality is the incompatibility of objects with this mirror image by any movements or rotations in a three-dimensional space. Thus, the configurations object divides into the right and left. Now, look at your hands. It's a simple example of chirality. No matter how we twist them, we will never make them exactly the same objects. And biomolecules also have the chirality property. Then you can ask me the following questions. What's wrong with this protein, prion, and how it's related with chirality? And I can answer. In normal form, prions are present on our nerve cells in every person and called PRPC. Neurodegenerative diseases is caused by a pathogenic prion protein called PRPSK. SK is a short form from scraping. And pathogenic protein can become if it's incorrectly stacked during the folding. An abnormal isoform of PRPC. The pathogenic structure of prion is more dominated by beta helix. You can see it in this picture. Thus, prion diseases of mammals and humans called conformational diseases. The development of prion diseases is very fast, and this is because pathogenic protein when interact with a normal protein, it's normal, and this is pathogenic. And when pathogenic protein interacting with normal protein, it can make its conformation to pathogen and turn out to PRPSK as a form. And this process is growing exponentially, like there. Thus, the main questions remains: what exactly causes incorrect prion protein folding, its mechanisms, and how to prevent it? And now I am ready to make a conclusion. The purpose of my work is to find relationships between protein folding, its possible violations, and changes in the chirality of the objects. As a consequence, to explain occurrence of neurodegenerative diseases as a violation of chirality. Dear colleagues, today I hope that I was able to open the veil of mystery as brain neurodegenerative diseases, and we will study this sphere more deeply at our next meetings. Thank you for your attention, and if you have some questions, I'm ready to answer them.
Yeah, thank you for the report. It's a pleasure for me to hear a beautiful lady talk about such small things, and while I was listening, question arose. How is chirality related to changes in prion conformation?
I understand. Let's go to the slide. 1 second. Yeah, this. Oh, no. Yeah, this. As we can see in the normal form, the prion structure more alpha helix, as I have said before. But in the pathogenic form, it makes more beta leaves, and it's turned to more and more pathogenic prion proteins, and chirality, when you describe alpha helix or beta leaves, they also have a chirality property as biomolecules. And my propose to understand how the chirality changes, whether it changes at all, and how they pass from one form in normal alpha helix to beta leaves in pathogenic configurations.
Thank you for answer.
Thank you for question.
Thank you very much. Dear colleagues, we have our last speaker on the agenda. Let me give the floor to him. So welcome, Maxim Lovegin.
Well, dear ladies and gentlemen, we are here today to share the information about our scientific directions, and I'm glad to see you all. Let me introduce myself to you. I'm Maxim. I'm a third-year undergraduate student of Moscow State University, physical faculty. I'm studying in quantum electronics department and working in the laboratory of quantum optical technologies. Now I'm going to present to you the field of science I'm working in. And here is the structure of my today's talk. Firstly, I will tell you about our laboratory in general. Secondly, I will consider a specific direction of my group. Further on, I will tell you about my research in the lab, and finally, I make a conclusion. The development of experimental methods of quantum optics has led to the emergence and rapid growth of a new field, quantum communication and quantum computing. The Laboratory of Quantum Optical Technologies is working on solving key scientific problems in the field of quantum technologies, creation of quantum cryptography and quantum communication systems, physics of cold atoms and their interaction with light fields, integral photonics, and quantum state engineering. The laboratory includes several experimental groups. Our group uses arrays of single rubidium atoms captured in optical dipole microtraps as prototypes of quantum computing registers. We create 2- and 3-dimensional arrays of microtraps using holographic optical tweezers. These arrays can be dynamically reconfigured, which allows us to create uniformly filled arrays of single atoms cooled to temperatures below 50 millikelvin. Such sublevels of hyperfine splitting of the ground state of atoms as logical states of qubits, we turn an atomic array into a quantum computing register of several dozen individually addressable and controlled qubits. The main task facing our group is the implementation of 1- and 2-qubit logic gates and the creation of a medium-scale quantum computer based on the atomic architecture that can demonstrate an advantage over classical computing devices in different applications, such as simulation of multi-particle quantum systems. My work in a laboratory is related to 2- and 3-dimensional optical tweezers. It is an important part in the creation of arrays of cold atoms, which will be set as qubits in quantum computers. The principle of operation of dipole traps is based on the induction of a dipole moment in an atom that interacts with a trap field. The main mechanism underlying the operation of dipole traps is a dynamic Stark effect. Laser radiation leads to a perturbation of the energies of the ground and excited states of the atom. There are different ways to create arrays of dipole traps. For example, the use of microlens arrays, acoustic deflectors, optical resonators, laser beam superposition using diamond gratings, and so on. However, taking into account the various requirements for working these arrays, the most interesting is the use of special light modulators, SLM, which, thanks to the structure, are able to create interference of light of various shapes and characteristics. Trap patterns are created by special algorithms that count masks on the computer, which are then applied to the SLM. There are several families of those algorithms. The most used may be called the Gebre-Saxton algorithms and the Fourier phase superposition algorithms on the left and on the right. You can see examples. The first family have a large number of variations, such as the random superposition algorithm, the standard, the weighted, the compressive sensing algorithm, and so on. But they all include calculation of the superposition of fields from each SLM pixel and calculating Fraunhofer integrals. The second mentioned family is based on creating a set of Fourier planes with a linearly varying phase. I would like, of course, to talk about all the theory of all the mentioned algorithms, but since the presentation time is limited, I will limit myself to demonstrating the basic calculation methods used in the standard and weighted algorithms, which you can now see on the screen. Now you can see how these algorithms works. The slide show the target distribution, the mask applied to the SLM, and the simulated distribution. You can see that the approach used allows you to generate arbitrary trap shapes. The results obtained using this approach are quite satisfactory. We can get arrays of traps with uniform distributed intensity with a deviation of several percent. At the same time, the number of iterations may not exceed 20, which allows them to be performed at high speed on FPGA or CUDA. You can also see images of the actual intensity distribution in the traps obtained using SSD cameras. You can also see the model of three-dimensional traps here. Today, I presented to you the science field I'm working in. Described techniques and methods are important not only for creation of quantum computer, but also for studying the physical processes in clouds of cold atoms, stimulate neurons, which is used in medicine, and for many other fields of research. I hope this presentation has given a little more information about these scientific fields and you enjoyed it. Thanks for your attention, and I may answer some questions now if someone wants me to ask.
I want to ask you a question. What are criteria that determine the use of SLM and not other devices you have mentioned?
Yes, there are several requirements that we have to consider. The first one is that the spatial resolution of our array needs to be in order of micrometers. Then we need to have a capability to work with time resolution about several milliseconds and less. Also, we need to have an access to all atoms in traps individually and easily reconfigure our array. Special light modulators fulfill all these requirements, and that's why we use them.
Thank you very much.
Thank you very much, Maxim. I think our conference has come to its logical end. I'd like to say thanks to all the speakers. I hope you will follow us with our future web.